Welcome to AI Paper Podcasts. We're the show that digs into the latest research for you, the AI researcher or ML engineer who needs to stay ahead.
Yeah, cutting through the noise.
Exactly. And today, we're tackling a big one, a question that might make you rethink how large language models actually work. Is that impressive reasoning we see? Well, is it maybe just a clever illusion?
We're talking about chain of thought, right? Co-key, where the model shows its work step by step.
Right, it looks incredibly smart. You see the steps, it seems logical. But what if it's more like a magic trick?
Well, that's exactly what the paper we're diving into asks. It's titled, Is Chain of Thought Reasoning of LLMs a Mirage? A Data Distribution Lens. It's from researchers at Arizona State University, Cheng-Shuai Zhao, Huan Liu, and others.
A mirage, that's a strong word.
It is. They're questioning if COTI is a real structured reasoning ability, what they call an inductive bias, or if it's just, really good at echoing the patterns it saw in its training data.
Okay, so our mission today is to unpack that. We need to understand this data distribution lens they're using and look at the evidence they gathered. They built this special setup, DATAALCHEMY.
That's right, DATAALCHEMY. Very clever. And yeah, we'll get into that.
Perfect. So for everyone listening, if you just need the quick 1-minute takeaway, here's the gist of it.
Okay, the headline is, this paper argues chain of thought in LLMs is mostly a brittle mirage. It's not real logical thinking.
Brittle meaning it breaks easily.
Exactly. Its success hinges completely on how similar the problem is to the stuff it was trained on. Any significant difference, and it starts to fail.
And they proved this using DATAALCHEMY.
Yeah, they built this controlled environment, trained models from scratch, and then hit them with tests that shifted the data distribution, different tasks, different lengths, different formats.
And the results?
COTI performance just tanks when you push it outside its training zone. It often spits out what they call fluent nonsense. Looks like reasoning, sounds plausible, but it's wrong.
Okay, so the big implications for you listening, especially if you're an AI practitioner, don't rely too heavily on COTI. Test rigorously. Especially out of distribution, ODE testing is key.
Right, and don't think fine-tuning is a magic bullet. It often just patches things for specific new data. It doesn't create true general reasoning ability. COTI seems to be pattern matching, very sophisticated pattern matching, but not abstract thought.
Okay, that's the rapid summary. Now let's really get into the weeds.
Let's do it.
So first, let's talk about why COTI seemed so powerful in the first place and where these researchers see the cracks. Remind us quickly, what is COTI prompting?
Sure. It's basically when you nudge the LLM, often with a simple phrase like, let's think step by step, to break down a complex problem into intermediate steps before giving the final answer.
And it works surprisingly well, right? For math, logic problems, common sense stuff.
Oh, absolutely. The empirical results were impressive. And that success really led many people to believe, or at least hope, that these models were actually starting to engage in, deliberate thinking, real inference.
But this paper throws some cold water on that. They have that really striking example, don't they?
They do. It perfectly illustrates the issue. They asked an LLM, Gemini in this case, the day the U.S. was established is in a leap year or a normal year.
Okay, seems straightforward enough.
And the response is fascinatingly flawed. It says, the United States was established in 1776. 1776 is divisible by 4, but it's not a century year, so it's a leap year. So far, so good, right?
Yep, 1776 was a leap year. Correct logic.
But then it concludes, therefore, the day the U.S. was established was in a normal year.
Wait, what? It just contradicted itself. It correctly identified it as a leap year, then called it a normal year in the conclusion.
Exactly. It followed the form of reasoning step 1, step 2, conclusion, but the actual logical connection wasn't there. It's like surface-level mimicry, fluent nonsense.
That really drives the point home. And this isn't the first time people have raised doubts, is it?
No, not at all. There's been prior work showing LLMs can get tripped up by irrelevant details or rely too much on surface word patterns. Performance often drops sharply on really complex multi-step problems.
And that illusion of transparency thing.
Right, where you could even show the intermediate steps are wrong, maybe manually correct them, and the model still arrives at the same final answer. It suggests the steps aren't actually driving the conclusion in the way we think. All these things were hinting that something wasn't quite right.
So what's the big new idea in this paper? What's this data distribution lens?
Their core contribution is shifting the focus. Instead of asking if LLMs can reason, they ask how the reasoning behavior relates to the training data. Their hypothesis is that connecting isn't a general skill, it's an inductive bias, learned from the specific distribution of data it was trained on.
Inductive bias meaning? like a learned preference or shortcut based on the data.
Precisely. It prefers solutions that look like the step-by-step examples it saw during training. And crucially, its ability to do this successfully is limited by the discrepancy between that training data and the new problem it's facing.
Okay, so it's less about pure logic, more about pattern matching and generalization from seen examples.
That's the reframing. Think of CutNT not as a thinking process, but as a very advanced pattern matching engine. It interpolates and extrapolates based on statistical regularities in the data. It works when the new problem is structurally similar to things it's seen before.
It can generalize, but only conditionally.
Conditionally, yeah. Based on similarity, not based on abstract understanding.
And they formalize this idea of discrepancy, something about Cale divergence.
They do get a bit theoretical, yeah. They talk about the training distribution, D-train, and the test distribution, D-test. Cale divergence is basically a mathematical way to measure how different those two distributions are. And they have a theorem, a generalization bound. The key takeaway for you is the expected error on test data is linked to the error on the training data, plus a term that grows with this distributional discrepancy.
So bigger difference between training and test data.
Bigger potential for error. More discrepancy likely means more failure. It puts a mathematical boundary on how well you can expect CoT to generalize if the data shifts.
Makes sense. And to test this systematically, they looked at shifts across 3 dimensions.
Yes. 3 key ways the data distribution can shift. Task generalization, can it handle new types of problems or structures? Length generalization, how does it cope with shorter or longer reasoning chains or inputs? And format generalization, how sensitive is it to just wording changes in the prompt?
And this is where DATAALCHEMY comes in. Why did they need to build a whole new environment?
Because real-world training data is messy, right? It's massive, uncontrolled. To really test these specific types of generalization, they needed a clean, controlled environment where they knew exactly what the model was trained on and how the test data differed. DATAALCHEMY let them train models from scratch under these precise conditions.
Like a synthetic lab for LLMs?
Exactly like that. It lets them isolate the variables.
So what are the nuts and bolts of DATAALCHEMY? How did they build these tasks?
It's quite elegant, actually. They start with basic building blocks, 26 basic atoms, just think of them as letters A to Z. An element is just a sequence of these atoms, like APL.
Okay, simple enough.
Then they define 2 basic operations, or transformations. First is ROT transformation. It just cyclically shifts each letter. So APLE with ROT plus 13 becomes NCCYR.
Ah, like a Caesar cipher, got it.
Yep. The second is a cyclic position shift, FPAs. This shifts the positions of the letters. APPLE with plus 1 shift becomes EAPPL. The last letter moves to the front.
Okay, 2 simple rules.
But here's the clever part. They can combine these transformations into sequences, like do a ROT shift, then do a position shift. This creates multi-step problems. A query might be, apply transformation sequence S to element E.
And the code AT steps are the intermediate result.
Exactly. If the sequence is F1, then F2, the code AT would look like E1, mirror E2, where E1 is the result of F1 and E2 is the final answer after applying F2. This makes the reasoning steps completely explicit and verifiable.
So they can check if the model actually followed the steps correctly, not just guessed the answer.
Precisely. It lets them see if the intermediate steps are faithful to the defined process.
And the experimental setup was rigorous. Small model, trained from scratch.
Very rigorous. A small GPT-2-style decoder-only model, 4 layers, trained from scratch. A standard tokenizer, very low temperature, almost deterministic output for inference to avoid randomness. And they measured performance using exact match, Levenshtein distance, BLEU scores looking at the whole chain, the intermediate steps, and the final answer. Super controlled.
Okay, let's get to the results. This is where the Mirage idea really gets tested. Task generalization first. Can CoT handle new transformations or elements it wasn't trained on?
Right, and they even quantify task difficulty with a metric, TGC, task generalization complexity. They theorize performance should drop exponentially as this complexity increases.
And did it?
Dramatically. They train models on specific transformation compositions, like F1, followed by F1. Then they tested on different levels of out-of-distributionness.
Levels, like what?
Well, in-distribution ID was the same stuff it trained on.
Yeah.
Then composition, CMP, using familiar transformations but in a new combination, e.g. train on F10, F1, F10, F2, F20, F1, test on F20, F2. Then partial O, POD, at least one new transformation involved, and full O, entirely new transformation types.
And the performance?
It plummeted.
Yeah.
Exact match accuracy went from 100% on ID data down to near 0 for CMP, POD, and OD.
Wow, near 0.
Near 0. But here's the kicker, the really insightful part. In the composition setting, CMP, the model could sometimes generate perfectly correct intermediate steps, but still get the final answer wrong.
How is that even possible?
It suggests the model isn't actually using the steps to derive the answer. It's generating plausible-looking steps and a plausible-looking answer separately based on patterns. But the logical link is broken.
That's the fluent nonsense again.
Exactly. Or, in some cases where the transformations happen to commute mathematically, it might get the right answer, but via a completely wrong sequence of steps. It highlights this deep disconnect between the apparent reasoning path and the actual result generation.
So convincing on the surface, but broken underneath. What about fine-tuning? Did giving it a little bit of the new data help?
Yes, and this is critical for practitioners. Just a tiny amount of supervised fine-tuning data, like 0.015% of the unseen data, could rapidly boost performance on those OD tasks.
So a little data goes a long way.
It seems so. But what it suggests is that the model doesn't need to learn abstract reasoning principles. It just needs to see a few examples of the new pattern to sort of add it to its repertoire. It reinforces the idea that it's about pattern matching, not deep understanding. The fine-tuning just expands the bubble of seen patterns.
Okay, what about element generalization? Training on letters AM, testing on NZ.
Same story, basically. Yes. Sharp performance drop. The model struggled with elements containing unseen atoms. BLEU scores went to 0 for completely owed elements.
And fine-tuning helped there too.
It helped, yes. But again, the generalization felt limited. It still seemed tied to the patterns that had been explicitly shown, rather than understanding the concept of any letter.
All right, moving on to length generalization. Input length, or number of reasoning steps, how did Kerr handle changes there?
Poorly, again. For text length, they trained on, say, 4 atom elements and tested on lengths 2, 3, 5, 6. Even small shifts caused failures.
What did the models do? Just error out?
They often tried to force the output to match the training length. If trained on length 4, they might add random tokens to a shorter answer or cut off a longer one just to match the length 4 pattern. No flexible adaptation.
Wow. So it learned the length as part of the pattern. What about the number of reasoning steps? Train on 2 steps, test on 1 or 3.
Couldn't generalize. It stuck rigidly to the number of steps it was trained on. Again, performance only improved if they explicitly included examples of the new step lengths during training or fine-tuning. It's learning sequences, not the logic of how many steps are needed.
Okay, last one. Format generalization. Minor tweaks to the prompt. How fragile is QT?
Very fragile, it turns out. They measured prompt similarity and then introduced noise adding, deleting, or changing words in the prompt.
And
QT performance was easily affected. Inserting random words seemed to have the biggest negative impact. But interestingly, changes to the core parts of the prompt, the actual element or the transformation names, had a much bigger impact than changes to the surrounding fluff text.
that suggests it's really latching onto those specific structural keywords.
Exactly. It's sensitive to the format, especially the key components defining the problem structure. It's not robustly understanding the intent behind the words.
And you might wonder if this is just because they used small models or a specific setup. Did they check for robustness?
They did. They tested across a range of sampling temperatures, from deterministic to more random, and different model sizes, from tiny 68K parameter models up to a respectable 543M parameter model.
And the conclusions held up.
Yes. The brittle Mirage phenomenon persisted across these variations. It's not just an artifact of one specific setting. It seems to be a more fundamental property of how CoT currently works, at least in these controlled experiments. Scale and temperature didn't make the fundamental pattern matching limitation go away.
Okay, so let's pull this all together. What's the big picture here? What does this mean for you, our audience of AI researchers and engineers?
Well, the central conclusion from this paper, based on their DATAALCHEMY experiments, is pretty stark. Chain of thought, as we currently see it, isn't genuine logical reasoning. It's more like a highly sophisticated, structured form of pattern matching.
A brittle mirage.
The brittle mirage, yes. It works well when the test data closely resembles the training data distribution. But push it even slightly outside that distribution. New task structure, different length, tweaked format, and it could break down dramatically, often producing that deceptive fluent nonsense.
So the practical implications. This is crucial. What should people do based on these findings?
First, be cautious. Guard against over-reliance on CoET, especially in high-stakes areas like medicine, finance, anywhere errors are costly. Don't assume the plausible-looking steps mean the reasoning is sound.
Human oversight is still critical.
Absolutely. Domain experts are essential for auditing these outputs. Second, prioritize out-of-distribution OD testing. Standard validation isn't enough. You need to actively probe the model's limits with tasks that vary in structure, length, and format from the training data. Adversarial testing, O-testing make it standard practice.
Find the breaking points before deployment.
Exactly. And third, understand the limits of fine-tuning. SFT can improve performance on specific new data points or formats, but it's often just expanding that in-distribution bubble. It's more of a patch than a path to true abstract generalization.
So, relying on SFT to fix every new failure case isn't really sustainable.
Probably not. It avoids the deeper issue, which is the fundamental lack of robust inferential competence. At the end of the day, Cale seems brilliant at replicating learned patterns, but not necessarily at understanding the underlying logic in a flexible way.
So this deep dive really underscores the brittleness behind the impressive facade of Cale. It's a powerful pattern matcher, but maybe not the thinker we sometimes perceive it to be. For you, the researcher or engineer, it's a crucial heads up.
It really is.
Yeah.
Which leads to maybe a final thought to leave you with.
Go on.
If today's chain of thought is largely this brittle mirage, what would genuine, truly generalizable reasoning in an LLM actually look like? What are the fundamental changes or breakthroughs we need to get there?
Moving beyond just pattern replication.
Right, to achieve real, deep, inferential competence. It brings up that big question for the future of AI. Are we ultimately building incredibly convincing simulators, or are we on the path to building true artificial thinkers? Something to ponder.